Morning, everybody. So at the end of the last lecture, we introduced Aldous' line-breaking construction of the Brownian CRT, which we thought of eventually at the end of the lecture as being embedded in L1. If you found that confusing, don't worry. That's the last time we're going to see that way of thinking about it. So the purpose of today's lecture is to come up with a sort of somewhat more flexible framework for us to think about continuum trees. Okay. So we started, great, thank you. So in the last lecture we had a sequence of discrete trees that had particularly nice properties, right? So we thought about a sequence of binary trees where we had this nice nested construction where at each stage of the construction we had a uniform sample from the set that we were interested in. And we saw that that sequence of trees which were generated by Rémy's algorithm had various aspects of them which converged to aspects of this line-breaking construction of the Brownian CRT. So you can, of course, think about taking that sequence of trees and embedding them in L1, just as we did for the line-breaking construction of the Brownian tree. And so let me state the theorem, which I guess is kind of the thing that you might expect, given everything I said in the last lecture. So I'm not going to prove this, but I think it would be bad of me not to at least state it. So in this form, this is due to Curien and us, which says that, so we saw that we needed to rescale distances in our plain binary ordered leaf label trees. I don't know, I've forgotten some word in that list, but you know what I'm talking about, the model that we had from the last lecture. So if I rescale distances in these things, so let me now think of a single edge in such a tree as having length 1. So when I want 1 on square root of 2n, I'm thinking about rescaling those edge lengths by 1 on square root of 2n. And now think about it in Rémy's algorithm. Every time I come along and I add a new edge, I'm going to add it in a new coordinate of L1, just as I did for the line-breaking construction of the CRT. And then we can make sense of the following statement. So this converges almost surely as n goes to infinity to the Brownian CRT. And what's the sense of this convergence? So I'm now thinking about these things as compact subsets of L1. Okay, and the right notion of convergence then is just the Hausdorff convergence. Okay, so in the sense of Hausdorff convergence, for compact subsets of L1. Okay, so again, if this isn't meaning much to you right now, don't worry. We're about to step away from this way of looking at it and think about a different way of doing it. So I'm not going to prove this theorem. I will later in the course deduce the convergence in distribution from a more general theorem that I will prove. Okay, so let me turn to the topic of today's lecture, which is, maybe let me put this here. So R trees and the Gromov-Hausdorff-Prokhorov distance. Oops. Okay, so something I meant to say at the start is yesterday afternoon I went back through the notes and I corrected all the typos that I found. So if you go to this page, you'll find a slightly corrected version. Question?
What is
it? Tn, so this is, do you remember we created a sequence of trees using Rémy's algorithm?
No, but is it embedded in L1?
Yes, so I'm thinking of it now as being embedded in L1 in exactly the same way as I did for the line-breaking construction of the Brownian tree. So in other words, I've got a first stick, so now my sticks are going to vary in length, so this is going to be a bit more complicated.
Those varying length.
Yes, so they have varying length. So, okay, so think about what happened. So we started with our first edge, Okay? And as the construction goes on, it's going to change in length, right? Okay, so in total length, and also I'm going to rescale by 1 on square root of 2n at each step. Okay, so remember that we had, if we looked at the distance between 0 and 1, and we rescaled by 1 on square root of 2n, this was a thing that was converging almost surely.
But did we scale t, the big T, like we defined it as being the closure of f of.
So this has already got the limiting lengths already in it. So let me remind you how we constructed this. Okay, so we took r plus, okay, and we split it up into real valued sticks in terms of length. So here was C1, here was C2, here was C3, and so on. Okay, so I took a stick of length C1. So what is this length C1 here representing? It's the limit, once I do Remy's algorithm over and over, and I rescale the length of this edge by 1 on square root of 2n. Right, so this thing here is representing the limit of the rescaled length of this edge between 0 and 1. Right, do you see? So I'm adding things along it, but I'm also rescaling by 1 on square root of 2n. Okay? And then you have to think about doing the same thing to the path that leads from this to 2. Okay? So that will have limiting length, which is given by this little interval here, and so on and so forth. Okay, no problem. Keep the questions coming. I'm very glad to have people who are paying attention. Okay, so today's lecture is largely going to be about R trees. Okay, so I want to put the definition over here so that we can refer to it later. Okay. So a compact metric space let's write it TD. This is not the same T as that one, but maybe actually, well, I don't know. There's only so many script T's that I can manage to write in chalk. Okay, so a compact metric space TD is an R tree if there are two conditions which are satisfied. So for any elements V and W of my metric space, so firstly, there exists a unique isometric map, so which I'm going to call FVW, which goes from the interval 0 distance between V and W into T, such that the start of this line segment here is going to get mapped to V, and the end of the line segment is going to get mapped to W. Okay. So we write, so this is going to be a definition. So the image under this function f of the interval 0 up to the distance between V and W, we'll write sort of double brackets interval VW. So let me immediately say what this is saying. This is saying that, so firstly, V and W are distance VW, dVW apart, okay, and this is essentially saying that the shortest path between them is a line segment, okay, so it looks just like the interval 0 up to dVW, okay, so there's an isometry between that and the path in the tree, or how I get from dVW. Okay, and secondly, if G is a continuous injection, let's say from the interval 0, 1 into t. If I write down here, can everybody see, or am I getting too low? Too low? I'm going to finish it here then. Can you see it? So let me just rewrite this. So if G is a continuous injection from 0, 1 to t, such that G of 0 is equal to V and G of 1 is equal to W, right? So this is going to be some other way of getting from V to W within my tree T, or my object T. Then the image under G of the interval 0, 1 is again this double bracket VW. So what I'd like to convince you of is that this is precisely the right sort of continuum analogue of what we think of as a tree in the graph theoretic sense. So this is saying that there's a unique geodesic from V to W, okay? And in fact, that geodesic looks like a line segment. And this is saying that's the only path for V to W. Okay. So let me put that up there. So there exists a unique shortest path from V to W, and it is the only non-self-intersecting path. So in other words, we don't have cycles, right? So this is the right sort of notion in order to be thinking of some sort of continuum notion of a tree. Okay, so because I've got this nice isometric map from this interval into the path between V and W in my tree, the right way to think about these things really is as intervals sort of glued to one another. Okay, so it's a nice way of thinking about the sort of object that we were creating, say, with our line breaking construction. Okay. So I should say that I'm very much in this lecture going to be following the survey paper of Le Gall on random real trees. I don't know of a better way to think about these things than he's already spent a lot of time thinking of. And so if you'd like to go and have a look at the master explaining it, so to speak, there's a beautiful probability surveys paper, which I refer to in the notes. So I don't want to claim any originality for this way of looking at things. Okay. So let me give us some terminology just so we can talk about these things. So I'm going to refer to a point in my metric space as a vertex, just by analogy with our normal graph theoretic trees. So we sort of have vertices but no edges now. Okay, so think about the picture we had with our discrete trees converging to the Brownian tree. All edges are getting squished to 0 in length. And so I've really just got points of my space left at the end, and there's no sense in trying to distinguish between edges and vertices anymore. I've just got points. Okay, so it's quite often going to be helpful, just as it was in the discrete setting, to think about rooting these objects. So that's just distinguishing a point. So a rooted R tree has a distinguished vertex. Which I'm always going to call rho. Okay. Because I want to think about drawing these things growing up from their roots, I'm going to refer to the distance between rho and V as the height of the vertex V. Okay. So ordinary trees have leaves, okay, and this is also going to be the true for these objects here. So what do I mean by a leaf? A leaf is a vertex, let's say V, such that V is not in the path from the root to W for any other vertex W. Except, of course, itself. Okay, so I'm going to write L of T for the set of leaves. Okay, so more generally, so in a discrete tree, we have a notion of degree for a vertex, and the leaves are precisely the vertices of degree 1. Okay, so we can make a more general notion of degree in these objects by asking how many connected components does removing a vertex split the space into. Okay, so the number of connected components into which the removal of V splits T is its degree. Okay. And again, by analogy with discrete trees, a vertex of degree 3 or more is a branch point. Okay, so for the moment this all feels very abstract. What I want to show you is essentially the standard way of generating R trees, and it's essentially the only way that we're going to generate them in this course, which is using continuous functions. Okay, so the setup is as follows. I'm going to let H be a function from R plus into R plus, and I not only want it to be a continuous function, but I actually want it to be an excursion, by which I mean I want it to start at 0, and I want it eventually to come back and stay at 0 forevermore. So let H be an excursion. So, i.e., a continuous function such that, so it's going to start at 0, okay, and I can define some zeta, which will be the first time that the function is 0 from x onwards. And I'm going to require, firstly, that this is strictly positive and that it's finite. Okay. So in other words, I'm thinking about things like this. Might come back to 0 and go away again, but eventually I'm going to stay at 0 forever. Okay, so that's a possible H. Okay. Now, of course, continuous functions can be considerably wigglier than the one that I've drawn on the board, but I'm going to try and keep my pictures fairly simple so that people understand what's going on. But maybe bear in mind that eventually I'm going to want to think about things that have properties similar to a Brownian motion. So I'm going to want to think about functions which are nowhere differentiable, for example. Okay. Okay, so how do we use such an excursion to generate an R tree? So let me tell you the idea and then give you a formal definition. Okay, so let's take this function that we've got here, and maybe I'll have a different colour of chalk. So what I want to imagine is you've got a glue stick, and you're going to come along and you're going to put glue on the underside of the function. Okay, and then what you're going to try and do is squish the two sides of the function together. Okay, and whenever two bits that have got glue on them meet, they're going to join. So I want to imagine squishing this whole thing horizontally and gluing it together. Okay, and so the idea is, whenever I see a local minimum like this, this is going to correspond into, well, me sort of splitting into two different parts, each of which have got glued together. So maybe let me try and draw the tree that this should give. So here I've got a branch point at the root, right, because this part of the excursion never gets glued to this part of the excursion. So that's precisely a branch point at the root. So here's my row. Okay, and then I've got one branch that goes all the way up to this local maximum here. And then I've got sort of quite a large branch which consists of this all squished together. And then here on this side, I've got a split here into two roughly equal length sticks. Okay. So my distances don't correspond very well, but at least hopefully the shape you can see is roughly the same. Does that make sense? Okay, lots of nods, that's good. Okay, so how do we do this mathematically? So I'm going to use the function h to define me something which is going to be like a metric, not quite a metric, because it's going to have distinct points which are at distance 0, so it's a pseudo-metric. Okay, so how am I going to do this? So let's give ourselves a bit of notation for the minimum of the function between two values x and x primed. So let's let mh of, I decided x and y apparently. So this is going to be, let me not assume that x and y are ordered. So this is going to be the infimum between the minimum of x and y and the maximum of x and y. Is everybody okay with my wedge and v notation for minimum and maximum? So this is the minimum of x and y, that's the maximum of x and y. And between those 2 points, I'm going to take the infimum h of z. Okay. So, for example, if my x is here and my y is there, then the z in question that minimizes is going to be this one here. Okay. And the value of the minimum will be whatever this value here is. Okay. So then I'm going to define, for the moment, d tilde h of x and y to be the value of the function at x plus the value of the function at y minus twice the minimum between them. Okay, so let's again have a picture. Maybe a slightly simpler one for the moment. Okay, so here's x, here's y, and here's the minimum. Okay. And what I'm saying is I'm essentially defining the distance, or pseudo-distance for the moment, between x and y to be what happens when I go down as far as the infimum between them, and then I go back up as high as the function. Right? So this is going to be eventually a branch point in my tree where the distance between x and y is obtained by going down to the branch point between them and then back up. Okay. And that's going to do exactly what my sort of gluing operation did. In a moment, what am I going to do? I'm simply going to identify points which are at distance 0. So which points are at distance 0 in this case? Well, those where there's no minimum between them. Okay, so I'm going to glue these 2 points together. These points are at distance 0 because the height of this one is the same as the height of that one, and that's equal to the minimum of the height between them. And so this whole thing is just going to give me 0. Okay, so the way I'm going to create my tree, or thing that will end up being a tree, is by quotienting. So make d tilde into a metric by quotienting. i.e. define, so let's say th to be the interval, this is my zeta, 0 zeta, quotiented out by the relation tilde, where tilde just puts x in relation with y whenever this distance is 0. Where x tilde is y if d tilde h of x and y is 0. Okay. So this quotienting operation is exactly the gluing that I showed you in my picture over there. Okay, so this gives me my space, and of course there's a sort of version of this which is on the tree th, and I'm going to take the tilde off in order to talk about that. So then dh is the metric induced on th, and it's now a true metric because I've put everything at distance 0 together. Okay, and I want to have some notation pi h. This is going to be the projection map. So this is the map that takes me from an element of the interval 0 zeta into this th here. Okay, so let me just observe something about this projection map. Because I started with a continuous function h, the projection map is also continuous. Okay, we're going to use that a few times in the sequel. Okay, so there's a kind of canonically obvious point at which I can root this object, right? I've got the point 0 here, and it would make sense to take that as some sort of root of this object. It's at the bottom in my picture, and I want to think about my trees as sort of rooted at the bottom. So we will usually root th at, so rho, which is the image of 0. And let me also observe that that's the same as the image of zeta. Okay. Right, okay. So I claimed that this was a way of creating an R tree, so we'd better prove that this thing we've just made does actually satisfy these conditions here. Okay, so I'm not going to do this in all the details. I'm going to draw lots of pictures, and I'm going to hope that that's actually a more useful thing to do and leave you to read through the details if you so wish. So I'll try and do it sort of reasonably slowly. So before I come to the proof, well, let me state the theorem first, and then we'll talk through some various aspects of these objects before coming to the proof. So theorem 3.2. So for any excursion h, this little metric space here is an R tree. Okay. So the first thing I'd like to do is not properly state, but talk you through a sort of intermediate lemma. Okay. So if you look over here at this definition of an R tree, we need to check for every pair V and W that we have these two properties here. And what I'd like to do is a quick reduction of that to one of those points being the root. Okay. It's going to make my life easier if one of my points is sort of pinned down to be a nice canonical one, and then I can just move the other one around. So in order to do that, we need a sort of rerouting lemma. Okay, so what this lemma is going to say in words is that if I move the root of my R tree to some other point, I can come up with an excursion that describes that, and the distances are preserved. Okay, so this is just, I can move the root of my tree to a different place, but I still get an object of the same nature, and I preserve the distances when I do that. Okay, so like I say, I'm going to primarily draw a picture for this, because the proof really is just chasing the definitions, and it's got a sort of slightly fiddly case split, but there's nothing terribly hard in it. It's just you've got to keep track of all the cases. Okay, so rerouting lemma. Okay, so let me try and stick to the picture I've got in my notes. So this is my excursion H. Okay. And this is my zeta. Okay, and what I want to do is I want to move the root from being 0 to being, well, whatever the image of this point x0 is. Okay. So I've just picked some point in the interval 0 zeta, and I want to move to being rooted here. Okay. And the way to do that is as follows. So firstly, I'm going to move the axis to here. Right. I'm going to copy this bit of the function over the other side. Maybe I'll have a third colour. It's high tech around here. So that sort of does that. Okay, so now again, I've got a thing which has length zeta here. Okay, and then I need to just play around with my function a bit. So the new function that I want starts just as the old one did, and it does something different. It sort of does, this straight line goes up here, and then I need to have a bit that comes down, and then I need to copy this interval here. I've gone too high, sorry. Okay, I haven't quite managed to line up. Let me fix this bit. Something like that. Okay, so I've done a straightforward operation to this function, and I've got back the thing which I'm going to call h primed. And my claim is that h primed is the excursion which encodes a rerouted version of my tree where I've rerouted at whatever the image of the point x0 is. Okay, so if you look in the printed lecture notes, you'll see the expression for this function h primed. Possibly there are people here who are much cleverer than me and can see just from looking at that function that it's this thing. But I find it quite difficult to see at first sight. But let's think about what's going on here. So in my original excursion, right, so this point above here, so this part of the excursion that's above the level of hx0, that's going to encode the subtree that's rooted at the image of x0. Okay, and then there's a part of the tree which is below that. Okay, so let's think about what's going on up here. So in my original tree, I've got the part that goes up from the root. There's a branch point here, And then there's another branch point here. So let me draw this like this. Okay, so that's roughly what my original tree is looking like. Okay, and I want to reroute somewhere here. Okay, so my original root is at the bottom. And this is my image of the point x0. Okay, so what you have to imagine is I want to now bring this down to the bottom. Okay, and it's now a branch point, right? Because I'm now thinking about it as having these two different paths leading off from it. Okay, and what are we going to get? We're going to get, so one thing that comes down to a branch point and then splits. And there's the old root sitting here. Okay. And then I've got another branch which comes off here and splits. Okay. And you can see that that's what this is doing, right? I've now got a branch point at the root. I've got, this part is actually in my picture, this bit. And then I've got this part as well. Okay. So I've just sort of moved everything around and put the point, which is the image of the point x0, at the bottom of my picture. Okay, go ahead.
But suppose that when you choose your x0, it's like in this valley between the first here and the second.
Suppose I put it here, at this branch point. Okay. So then I've got a branch point at the root, that's fine. Okay, so I'm then going to be copying this part of the function over here and then playing around with it so that I'm reading things in the correct order, basically. You need to do some flipping because sort of what was up sometimes becomes down in the new picture. Yeah, exactly. Okay, so I encourage you to play around and draw some pictures for yourself. I think that's probably much the easiest way to get a hold of this. Okay, so if that didn't make any sense, don't worry. All I'm saying is it's going to be sufficient for me to check root plus other point rather than having to check any arbitrary pair of points. Okay, right. So I just need a little bit more terminology before I can get to the proof of this thing. Okay, so we've got this metric space THDH. Okay. So I want to define a partial order on this thing. Okay, so how am I going to do this? I want to say that if I've got a pair of vertices V and V primed, I'm going to write that V is less than V primed in this partial order if it's the case that the distance from the root to V primed is precisely the same as the distance from the root to V plus the distance from V to V primed. Okay, so these are points, pairs of points, such that there's equality in the triangle inequality coming from the root. Okay. So if this is the case, I'm going to say that V is an ancestor of V primed. Right, so it's on the way to V primed and it's closer to the root. Okay. So I'm thinking of the root as the sort of progenitor of this whole population, and I'm thinking about gradual descendants going upwards. Terminology for trees is extremely confusing. Descendants should be down, right? But in this context, my descendants are going up. Okay. It's a family tree in the usual way that we would draw them. Okay. So for any pair of points, x and x primed in, let's say, 0, zeta, open at the zeta end, which are such that, well, the image of the image of x is v, and the image of x primed is v primed. Okay, well, what must be true if we've got this? Well, the distance between v and v primed, well, firstly, that's exactly the same thing as the pseudo distance dh tilde between x and x primed, because x and x primed are pre-images of v and v primed under the projection. Sorry?
In the identity on the right-hand side, the subscript should be dh rho v equal dh rho v plus dh v prime. It's only rho.
Sorry. Thank you. Thank you. Yes. So this is dh, the distance on the tree. Thank you. Keep them coming. Great, where was I? So if this is the case, so if I've got this for these 2 points, then it must be the case that this is actually equal to h of x primed minus h of x. Okay. And if you think back to how we defined this thing, this is the case if and only if x is the minimum point of the function between x and x primed. Okay. Okay. Right, so you can check that this gives you that this relation here is reflexive, transitive, and antisymmetric. Okay, so everything that we need for partial order. Okay, so if I've got a pair of points again in TH, I'm going to write so again, this sort of double square bracket VV primed for a set of W in TH such that DH of VV primed is equal to, again, such that the triangle inequality is tight. Okay, so that if I look at the path between the root and the vertex V primed, then that's precisely the set of V, such that V is less than or equal to V primed in my partial order. Okay, so I'm using the same notation I used over there, and part of the proof is going to be showing that these things really do coincide, right? That these really are the same notion of the path between, in this case, rho and V primed, and in this case, V and V primed. Okay. So maybe just let's think about this in terms of the original kind of interval 0 up to zeta. This is the same thing by what I wrote here as the set of x such that the minimum between x and x primed is h of x, where x primed is such that the projection of x primed is v primed. Okay? And I can take any such x prime, so any pre-image of this point. Okay, so like I say, I'm going to check that this one coincides with that definition over there as part of the proof. Okay, so I think there's one final, or a couple of final bits of definition that I need. Okay, so I want to think about the branch point that separates two vertices of my tree. Okay, so let's do that. So suppose again, V is the image of some point x, and V primed is the image of some point x primed. Okay, so then, if I take the collection of ancestors of V, and I intersect that with the collection of ancestors of V primed, well then, that's necessarily going to be, well, some path up to W for some W. And this W is what I'm going to call the most recent common ancestor of V and V primed. So W is the projection of some point Y for any Y such that, well, what needs to be true? The minimum of my function h between x and x primed is achieved at y. Okay. So I'm going to write, so v min v primed for this w, and call it the most recent common ancestor. So that's quite a mouthful. So most recent common ancestor of V and V primed. Okay. Okay, so we've thought about the collection of ancestors of a point. What I now want to think about is the collection of descendants of a point. Right? So we've thought about how we get from the bottom of the tree up to V. Okay, so that's this set here, if I go up to V primed. And I now want to think about, well, what comes after that? What's the subtree that's rooted at that point? Okay, so define. So th square brackets V. This is going to be the set of points V primed such that V is an ancestor of V primed. So these are the descendants of V. Okay, so let's think about this in terms of what gets projected onto this. So this is the projection of, well, the set of points x primed such that the minimum between x and x primed is given by x for any x such that V is the image of x. Okay. So I take some representative of the equivalence class that's giving me V. Okay, and I ask which of the points x primed such that the minimum of the function between x and x primed is achieved at x. Okay, and that's going to be the subtree that's rooted at V. Okay, so let's just think about the properties of this set here for a moment. So if it's the case that this thing is not just the singleton V, okay, so it's possible that we're at a leaf, right? In which case there are no descendants of my vertex V. Okay, But if that's not the case, and if it's also not the case that V is the root, then if I take this set and remove the root, remove V from it, and if I look at the whole tree without the subtree rooted at V, then these are disjoint non-empty sets. Okay. So what I'd like to argue is they're also both open sets. So let's again have a picture. Okay, and I'm interested, say, in this point here. Okay, so there's the subtree, or rather the descendants of, so this is X, where X projects to V in my tree. Okay, so we've got this set of stuff up here, okay, which is going to be the descendants of X, and then there's going to be everything that's coded by the rest, okay, all of the bits that I haven't included in that. Okay, and you can see that this is precisely the set of points such that h of x is the minimum between x and that point. Okay, so this really is the set of descendants of that point. Okay, so my claim so if I remove V from this set, and if I look at the complement in the whole tree of this thing, these are open. Okay, so let's do this one first. So again, let's take X be such that it projects to V. So then we've got that this set here, sorry, I think I'm doing this one first. Hold on a sec. I've confused myself in my notes. Let's do this first. Okay. So I want to show this is open by showing that this thing is closed. Okay. So the whole thing is closed. If I subtract this, I'm going to get a closed, open thing. Okay. So th of v. So we can think about this precisely just, as I said over there, of the projection of the set of points x primed, such that the minimum between x and x primed is h of x. Okay, so this is a compact set. Okay, again because h is continuous. This is a continuous function, and so the continuous image of a compact set will be closed. Okay. So hence, that's open. Okay. All right. And so now let's look at this thing. Maybe I'll move over a bit. So if I think about this minus v, okay, well, let's think about an element of this set if I take some other v prime that's in it, well, it's the case that the open ball of radius distance between v and v primed is entirely contained within it. Right? And since that's the case for every element of that set which is not equal to v, it must be open. Okay, so in other words, if I have a point in my tree which has non-empty set of descendants, then when I remove that point, I'm splitting my space into at least 2 open bits. Okay? Right, I'm not saying that these guys are connected, the 2 of them. Okay, so I'm disconnecting into at least 2 open bits. Okay, so this tells me that the degree of my vertex v in that case is at least 2. Right? I'm splitting into at least 2 disjoint bits. Okay, so I think we're now in a position to sketch the proof of the theorem, which has been long rubbed off the board. So what was the theorem saying? So the theorem says that this construction gives me an R tree. Okay, so we've got 2 things we need to check, which are these 2. And I'm just going to sort of sketch how you go about this, because I think probably everybody is feeling a little bit kind of overwhelmed at this point. I know I am. Okay. Right. Okay, so let's say proof in inverted commas. Okay, so the first thing to say, which I probably should have said over here somewhere, is that this is compact. The projection is continuous. So the tree itself is compact. Okay, so just to make a comment about what's coming in the future in a moment. So we're going to think about doing this with interesting random functions, h, in a moment. And we're going to get compactness for free from this argument. Okay, so something that when we were thinking about all this is line-breaking construction of the Brownian continuum random tree, and we worried about whether this thing converged in a nice way to a compact object, we're going to get the analogous result for free in a moment, which is very nice. Okay, so my claim is that by the rerouting lemma that I didn't really state, it's sufficient for me to take one of my points equal to the root. Okay, so let's take it to be W because I prefer the letter V. Okay, and again, let's have a toy function. So condition 1, what do I need to show? I need to show that there exists a unique isometric map, so f rho v now, okay, which goes from the interval 0 up to distance between the root and v into this t, which starts at the root, ends at vertex v, and which is an isometry from the line interval, from the line segment. So let's have a picture here. And the point is I'm just going to give you an explicit map F. Okay. So let's suppose that's my function h. Okay. So let's fix our v. And suppose, again, that x is some point which projects to v. Okay, so let's suppose that x is here. Okay. Now, of course, this point also projects to v, right? Because it's at distance 0 under my pseudo-metric. Okay. So note that the distance from rho to v is then precisely h of x. Okay. So now let me make a definition. So let's say x of r is going to be the smallest value of y in the interval 0x such that the minimum of the function h between x and y is precisely equal to r. Okay? And this is going to be as r varies between 0 and h of x. Okay. So let me try and draw x of r. Is the yellow visible, or should I use a different colour? Maybe let me try doing this with red instead. Oh, that's better. Okay, so this here is h of x. Okay. And that's the distance of this point from the root. Okay. And what I'm asking for is that for every r between 0 and h of x, there needs to be some x, here, x of r, right, which is at that height. Okay. So what I've drawn here is actually a representation of a collection of x's which are going to project onto being the ancestral line of the point V. Okay? So for every point down here, so this point here is precisely at the distance r from the root, okay? And it is the minimum of the function between it and x, okay? And so the red line here is a representation of, so a collection of points which project onto this thing here. Right, so it's not unique, of course, right? So I've got multiple pre-images for points in my tree. So what might have been another way of going about this? I could have said, well, let's take the largest such. So here's another way of doing it. Right, so if I take this bit and this bit, and that's going to project onto the tree to give me the path between the root and my vertex V. But it's also the case that if I take this chunk and this chunk and this chunk, and that projects onto the path, this set of ancestors of the vertex V. Okay, so my claim is that if you write this down properly, that gives you precisely this isometry from an interval of length d rho v into my tree. Okay. And I've just taken sort of going left rather than going right because I needed to make some arbitrary choice at some point. Okay. So my claim is, so firstly, all of these points are definitely in the set of ancestors of the vertex V, right? Because they are the minimum of the function between this point and the vertex I was interested in, which is the projection of x, right? And my claim is that, in fact, this thing here can't contain anything outside that set of ancestors. So it is precisely the set of ancestors between the root and the vertex V. So I need to show that if G is some continuous injection from 0, 1 into my tree, which starts, so let me correct this to be what I actually want to show, at the root and goes to V, then the image of that really is the set of ancestors of the vertex V. Okay, so G is continuous. My interval 0, 1 is connected. And so it must be the case that the image of the interval 0, 1 under G is also connected. Okay, so this is what I'm going to contradict in a moment. Okay, so I first show that it's the case that this set of ancestors of the vertex V must be contained in the image under G of 0, 1. Okay, so let's suppose not. So in other words, there exists some W which is in the ancestral line, which is not in this image here. Okay, so if that's the case, then it must be that this image set is contained in, well, the union of the subtree rooted at W, but not including W, with the rest of the tree. Okay, so this is the subtree, the descendants of W, but not including W itself. And this is everything that's not a descendant of W. Okay? And if W isn't in this image, then this image must be contained in the union of those two sets. But we said that these were disjoint open sets. Okay? So that contradicts the connectedness of this image, G0, 1. Well, I do need to check that I've got at least some part of this in here and some part of it in there, because otherwise it might be that I'm entirely within one bit. But the point is that G of 0 is certainly in the bottom bit. And G of 1, well, that's V, and that must be in the top bit. Right, since W is in this set of ancestors, right, so it must be that G of 1, which is V, is somewhere up in its subtree. Okay. But this contradicts connectedness of this set. Okay. So, one last thing to do. So now suppose there's an S in the interval 0, 1 such that G of S is not in the set of ancestors of V. Okay, so let's write W for G of S again. Okay, so W isn't itself in the set of ancestors, but there's a sort of closest point which is the most recent common ancestor between V and W. Okay. So let's consider this branch point between V and W, and that definitely is, by definition, in the set of ancestors of V. Okay. So it's definitely in the set of ancestors of V, and since it's the case that the distance between V and W is precisely the distance from the most recent common ancestor to V plus the distance from the most recent common ancestor to W, we not only have that V min W is in the ancestral line of V, but it must also be in this path from W to V. Okay, but then it must be the case that I encounter V min W before I encounter W. So V min W is in the image, not now of 0, 1, but of 0 up to S under G. And again, I'm going to use my rerouting trick. At W. It's also the case that V min W is in the image of S up to 1. Okay. But since G is injective, it must be the case that G of S is equal to the most recent common ancestor of V and W. Okay, so I don't visit anything more than once, right? So I must be visiting this at time S, which contradicts the assumption that W was not in the set of ancestors of V. Okay, so that, hopefully, in a reasonable amount of detail, is the proof that this really does give us an R tree. Okay, so I wanted to spend a reasonable amount of time on this because although we're not, again, going to deal with these things in quite such explicit detail, this really is the construction that's going to underlie all of the scaling limit objects that I'm going to talk about in the rest of the course. And I thought it would be a bad idea to just kind of skate over exactly what sort of thing we're talking about. So I'm sorry for spending quite so long doing sort of fiddly analysis at you, but I hope that when we come to sort of thinking about the objects that we're going to be dealing with as actual limits of our trees and graphs, this will prove to have been a useful exercise. And you can tell me afterwards if you agree or disagree with me, and I'm very happy to hear feedback. Okay, so what I want to do now, in my remaining sort of 8 minutes, is just have a quick chat about degrees of vertices, and then if I get a chance, I want to talk about measures. Okay, so Right, so how can I have a vertex of degree more than 3? Well, this is how. Okay, so imagine you've got, so this is a very caricatural function because it's only got one local minimum, right? But I want to sort of illustrate the point as carefully as I can. So I've got this whole collection of points here, all of which are going to map to the same point in my tree because there's no minimum between them that's not equal to themselves. Okay, so if I've got the situation that V in TH is not a leaf or a root, so if it's not a leaf or the root, what did we say? We said that, well, firstly, the pre-image of the set V must have at least 2 elements. And then there's a smallest one and a largest one. Okay, so let's give those names. So this is going to be the smallest element of that set. And let's let D of V be the largest element of that set. Okay, so on my picture, this one's D of V, and this one's G of V. Right. This is gauche and droite for the Anglophones in the room. Okay. So then I can write the subtree that's sort of rooted at this point here, which is this common thing here, or rather, if I remove that point from the set of its descendants, so this is the set of its strict descendants, that's going to split into different open intervals, each of which is going to correspond to a little sub-excursion that goes above that level. Okay, so then we can write so if I look at the set of x between 0 and zeta, such that my h of x is strictly bigger than the distance between rho and v, then that decomposes into a collection indexed by, let's say, I of open intervals AI, BI, where this is the set of connected components which make up, so where these are the connected components of the set. Okay, and the components of the subtree rooted at V, but not including V itself, are then the image under the projection map of these guys. And of course, let me not forget the bit that's below. Okay. So each of these is now connected, right? Because I said that these were the connected components of this set here, right? And I'm applying a continuous function to a connected set. And so these are connected in each case. Okay? So these are precisely the connected components into which I split when I remove the vertex V. Okay? So in particular, the degree of my vertex V is whatever the size of the set I is plus 1. And of course, there's nothing stopping the set I having infinite cardinality, right? In which case, I've got a vertex of infinite degree. Okay? So each of which is connected. So the degree of my vertex V is the size of I, which could be infinite, plus 1. Okay. Right. So in my final 2 minutes, I just want to say just one word about probability measures on these things. Okay, so for the moment, I haven't done anything random in this lecture at all. I've just been thinking about how you can make R trees out of continuous excursions. And we're going to apply this in a random setting next lecture. Go ahead.
Can't you just say that the degree of V is just the number of points in the pre-measured V by pH?
-1, I guess, or +1? Yeah, no, including. Yeah, I guess that works also. Yeah. Except if my function is constant. Elise makes an excellent point. Right? If my function is constant, this doesn't work. Right? So I really do want to be counting connected components into which I split things. Thank you for rescuing me. Great. Okay, so yeah, there's nothing stopping my function being flat. Okay, so here's an example of one of these functions. And so next lecture, I'm going to take my function itself to be random. But one thing I'm going to be interested in is how I might pick points in the tree. And I want some notion of a uniform measure on the tree. And there's a very natural way to do that, which is just to take, so I've got an interval here of finite length zeta. There's a perfectly good uniform distribution on that interval. So pick a uniform point on 0 zeta and just see where it projects on the tree. So it's a very natural way of sampling points in an R tree. Okay, so a uniform measure is obtained by sampling, say, U, which is uniform on 0 zeta, and then taking the distribution of wherever that lands on the tree, so pi h of U. Okay, so this induces a distribution on my R tree, TH. Okay, and that's going to be very useful to us because we're quite often going to be interested in sort of typical distances. Okay, so how might I characterize a typical distance? Well, one way to do that is to say, let's pick 2 uniformly random points from the object and ask how far apart they are. That seems like a good notion of a typical distance. Okay, and this gives us a mechanism for sampling those points that we can then talk about how far apart they are from one another. Okay, that seems like a good place to stop for today. Thank you for bearing with me.